Okay, thank you. Thanks to organizers, of course, a very nice group of organizers from different parts of the world. The main topic of my talk will be totaling on free actions and use of them for constructions of so-called invariant random subgroups. But I will try to touch also some other topics if time will permit. So let D be a dynamical system consisting of a group acting on a measure space by measure mu preserving transformation. In my talk, group G will be countable, and the measure mu will be a probability measure. So the important notion for such action is notion of ergodicity, which also already was mentioned many times, but let me recall that action is called ergodic if every invariant subset of X has measure either 0 or 1. So again, measure is probability, and if you have subset in X which is G invariant, then measure should be 0 or 1. This is a definition of ergodicity. I will also, some moment, will use notion of weak mixing, which is stronger condition. I will define it later. With such dynamical system, one can associate representation, unitary representation, pi of G in U L2 X mu, which already was used in several talks. Just, I will call it Koopman representation. I know that TV doesn't allow to watch well, and this representation is defined by the following relation. So group where F is a function in L2. So group X just by shifts on functions. This is classical Koopman representation. No, name of Koopman was mentioned in Amos' talk, maybe associated with publication of 1930. Important thing for actions with a probability measure is a constant function is invariant. So one can consider subspace orthogonal. So 0 means orthogonal to constant function, is invariant subspace. And the ergodicity of action is equivalent to the fact that there is no, that only constant functions are invariant. In other words, a restriction of Koopman representation on this L2 has no non-zero invariant vectors. Okay, what are other types of representations that one can associate? Regular representation was already mentioned. So this is a representation in L2 on G, group X by left shift, left regular representation, or right regular representation. The generalization of this is a quasi-regular representation, which I will denote this way. So if H is a subgroup, not necessarily normal in G, you can consider a set of cosets. Group X, say left cosets. Group X naturally on this set of cosets by left multiplication. You get permutation representation in L2 on the set of cosets. So this is quasi-regular representation, which is a generalization of regular. Regular corresponds to the case when a subgroup H is study group actions, mathematicians assume that action is free, or essentially free. So with action, one can associate the following objects. First of all, for element G, one can consider the set of fixed points for this element. So it's a subset of X. Secondly, with a point, one can, with a point of the space, one can associate a stabilizer of this point in a group G. It consists of those elements in a group which fix X. And this is a subgroup in G. Not necessary normal. And action is, so dynamical system action is essentially free if for every non-trivial element, measure of the set of fixed points is 0. Or equivalently, for stabilizer of X in G is trivial group, mu almost sure. So stabilizers of almost all points are trivial. And as I told, usually assumption on freeness of action is made in many considerations. Now, 5 years ago, Anatoly Vershik, mathematician from St. Petersburg, came with an unusual concept, namely concept of totally non-free action. And D is totally non-free. I will use this abbreviation. If there is a subset in X full measure with the property that stabilizer of different points in G are distinct. So basically, essentially, stay for this, that not maybe for all pairs of points, but mu almost sure, different points have different stabilizers. So this is extreme opposite to freeness. In the case of freeness, we assume that stabilizers are trivial. Here we suppose that different points have different stabilizers. So if a group acts on big space, on Lebesgue space, on space which has uncountably many points, and measure is continuous, it in particular implies that to possess such action, a group has to have uncountably many subgroups. Not every group satisfies this property. And the first problem that I would address is what groups allow faithful, totally non-free action on a Lebesgue space, say. You can address this question in case of locally compact groups, but today I restrict just on discrete groups. And as I told, first abstraction is the cardinality of the set of subgroups. Why totally non-free actions are interesting, and if there are groups which have such action, let me just indicate that if we consider map which associate with a point X stabilizer of this point, and this is point in the space of subgroups of the group G, which I will consider in more details later. So this allows to different points of the space to associate different subgroups. and such, and then take image of a measure mu under this, say phi star, and this will give invariant random subgroup. So one of things that you should catch at this point is that totally non-free actions lead to invariant random subgroups, which will be defined soon.
I'm sorry, the condition for the measure of x or not, it's full measure of z, yeah?
Repeat again.
The measure of x naught is 1, yes?
Yes.
In the other case.
Yes. So this map which define almost everywhere. Okay, so the totally non-free actions are useful because they lead to invariant random subgroups, but also they lead to so-called factor representations. I will try very quickly to say what this means, but before let me additionally to Koopman representation to define the so-called groupoid representation, which I will denote rho. Groupoid representation. This will be representation in the space A2R nu, where R will be a subset in X cross X, and will consist of pairs X GX. So this is an equivalence relation which corresponds to partition on orbits. Okay, and measure nu is roughly speaking a mu cross-counting measure. So if this is X cross X, this is our set R, then above each point there is only countably many points. Namely, what we see here is just orbit under action of G of point X. And the measure nu, in horizontal direction, is mu, and in vertical is just number. If you have a subset A, to know what is measure A, you just integrate number of points in section for all X, integrate through measure mu. And rho X on a function in this space, just by shift of the first coordinate. So this is left groupoid representation. Similarly, you can act on the second argument. Okay, so this is a groupoid representation. And now the fact is that with every unitary representation, you can associate the so-called von Neumann algebra. And von Neumann algebra is called a factor if centralizer is trivial, consists of scalar operators, and representation, any pi, rho, or whatever. So pi stay for Koopman representation. I don't know what sigma. Maybe you, so for unitary representation sigma, you can associate von Neumann algebra. Algebra generated by this unitary representation. Algebra is a factor if centralizer is trivial, or only scalar operators. And representation is called factor representation if this algebra is a factor. And such a representation play an important role in various studies, in study of von Neumann algebras and so on. And theorem of Grigorchuk, I do not formulate in a full like a theorem, but corollary of theorem of Grigorchuk is that if Gx mu is totally non-free, then von Neumann algebra generated by groupoid representation is a factor. So rho is factor representation. Groupoid representation coming from totally non-free actions are factor representations. Maybe. There is one more. So again, let's go back to to our space X, group acting on it. For each point X, you have orbit of this point. And therefore, you can associate unitary representation rho x. It's a representation on L2 on orbit, or on orbit of this point. Group acts by permutation of the points of the orbit, so you get, again, permutational representation. I denoted rho x, it depends on point x. And this is nothing else as a rho g of a stabilizer of the point. Quasi-regular representation corresponding to pair group and the stabilizer of this point. So here we have a field of unity representations, just to each point of the space corresponds quasi-regular representation. So now what we have? We have Koopman representation, we have groupoid representation, we have family of quasi-regular representations. If action is essentially free, this representation rho x are nothing else but just a regular representation. But in general case, they are different, and they can be different for different points, and so on. And one of important problems is given an element M of group algebra of a group, which is just a linear combination of elements of a group with some real or maybe even complex coefficients, but finite combination of this sort. You can, and given any representation, sigma of this sort or any other, you may be interested in the spectrum of corresponding operator. You apply this unitary representation sigma to element of group algebra, and you are interested in spectrum. In spectrum, in norm, and Amos in today discuss a lot of this type of things in certain situation. So if time will permit, I will formulate very recent joint result with Artem Dudko, which tells what may happen with spectra of the same element of group algebra if we apply pi, rho, or rho x. But it will be at the end. Now, one more thing that I forgot to mention is that if you have, again, totally non-free action, you may consider function on a group, which is just a measure of the set of fixed points. And if you denote it kappa of g, or chi of g, this will be what is called a character on a group. Character on group. Character is a function normalized by conditions that value at point 1 is 1. It's a constant on conjugate classes, and it is not negatively definite. And moreover, in this case, because in case of totally non-free action, the value of this function will be the same as value of trace on von Neumann algebra evaluated at point G. And character will be indecomposable, not linear combination of other characters. So indecomposable characters, they correspond to quasi-equivalence classes of factor representations of a group. So study of characters, as you understand, is an important issue. And some groups have many characters, and some groups have very little indecomposable characters.
Sorry, I missed what is sigma?
Sigma, any unitary representation. For instance, but my interest is mostly in sigma belonging to this set of representations. Now I am going to give examples of totally non-free actions. And the example is as following. Maybe let me erase this. And this is a group generated by 4 involutions, defined by me in 1980. Group X on interval 0, 1 by Lebesgue measure presenting transformation. generator A is just permutation of 2 halves of the interval. So I delete from interval the adic rational points. B, C, and D are defined slightly more complicated. We divide interval into 2 parts, then again, and so on. So we repeat this procedure of infinity many times, and we write sequence PPI periodically repeated. And P means, like here, is permutation of the halves of the interval over which letter is written, while I means identity transformation. So C and D are defined in similar fashion, just using a sequence PIP, IPP. So what are properties of this group? It's infinite torsion to group. So this is the simplest example of so-called Berside group related to Berside problem. Its element is amenable, but not elementary. Amenable. The question about existence of such group was raised by Day in 1956 and was open for a long time. Has intermediate growth. Between polynomial and exponential. Question was raised by Milner and answered by me. Is just infinite. It means it is infinite group, but every proper quotient is finite. At the same time, it's residually finite. So it has many finite quotients, but group is infinite, every quotient is finite. No, finally, it is branch. I will try to explain. It is automaton group, etc. So it has many properties, but the most important for this talk is that this group acting on interval 0, 1 and taking Lebesgue measure, mu, action is ergodic and totally non-free. So here we have concrete example of a group nicely defined which act totally non-free. In fact, it is now more common to view this group acting on a binary rooted tree, infinite binary rooted tree. Acting on such a tree, you can easily see how to transform action on the interval 0, 1 to the action on such a tree by automorphism. So A just permute these 2 vertices and no action inside, while B fixes these 2 vertices, X here as A, then as identity, and so on. So it's very simple automorphism of rooted tree. And for this model, it is nice. So acting on the tree group acts also on the boundary of the tree, which is just a set of geodesic rays joining root with infinity. And this boundary can be naturally identified with the space of binary infinite sequences. And group acts on the boundary by homeomorphism. So we have a topological dynamical system. And it preserves uniform Bernoulli measure on this space, half-half Bernoulli measure on this space. So we have action of this sort. And in fact, this dynamical system is just isomorphic to this dynamical system. Now, I have to explain what means branch very quickly and formulate fast result.
So excuse me, so this exact action is totally non-free?
This exact action is totally non-free, and in fact, in 80 I constructed this group as infinite torsion to group, very simple example, but then later I generalized this example to the family G omega, where omega is ternary infinite sequence, And all these groups basically satisfy the similar properties, and all of them act totally non-free. So, so there are many such groups. In group theory, so in the last 2-3 decades, like new classes of groups were defined and attracted attention because interesting, sometimes remarkable properties. So one class is class of branch group. Other class is automaton groups, which were studied already in the school of Glushko, some name known in computer science, automaton groups. Now another keyword is self-similar groups, related to study of fractals. Then the so-called iterated monodromy groups arising in study of rational polynomial mappings, so association with the study of Julia sets and so on. So what is branch group? Group is branch if there is spherically homogeneous rooted tree, generalization of binary rooted tree, with the property that group has faithful action on such a tree, and for every n, index of rigid stabilizer of level n in a group G is finite. So what is rigid stabilizer? Okay, spherically spherically homogeneous tree means that from level to level you can have a different branch number of points, but for all vertices of the same level, branch number is the same. Now, what is rigid stabilizer? You take any vertex, you consider subtree below this vertex, TV, and you consider in a group, so group X faithfully here, you consider those elements which act non-trivially on this tented path, on this subtree. So outside, action is trivial. All vertices are fixed. This is called rigid stabilizer of vertex V. It can be a trivial subgroup. Now we take rigid stabilizer of level n, so assume V belongs to level n. Rigid stabilizer of level n is just a group generated by rigid stabilizers of vertices V, which belong to level n. So we take different vertices corresponding rigid stabilizers and generate by them rigid stabilizer of level n. I forgot to add one more important thing is that action is level transitive. Level transitive. So, because a root vertex is fixed point, action on such tree cannot be transitive. But it can be level transitive, transitive on each level. And transitivity on levels, it corresponds to ergodicity of this dynamical system. Minimality of this system, unique ergodicity, and so on. So level transitive are especially important case. And if action is level transitive, rigid stabilizers of different vertices of the same level, they are conjugate. And so, in fact, in this case, this group is nothing else as just a direct product of copies of the same group. And now we insist that this rigid stabilizer has to be not only non-trivial, but have to be large in the sense that have to be have finite index. And another notion is weakly branch. Generalization of this notion. Weakly branch, when we just assume that for every vertex, so again, level transitive, for every V, a rigid stabilizer of V is non-trivial. So this is weaker condition. And the simplest example of a group which is weakly branch, but not branch, is a group called Basilica. And this is iterated monodromy group of polynomial z square minus 1, and it is a group generated by certain free state automaton I have no time to explain this, but group, so this is automaton group generated by certain free state automaton of a binary alphabet. So it is a weakly branch, but not branch. Now, why branch groups are interesting? There are a few reasons. The main is that the class of just infinite groups, which is important, clearly. First of all, due to the fact that if you have finitely generated infinite group, then it can be mapped surjectively onto just infinite group. So if you are looking, if there is some group that satisfies certain property, which is preserved under factorization, if such a group exists, it exists in the class of just infinite group. And there is theorem which claims that class of just infinite groups naturally splits into three subclasses. One is related to simple groups, one is related to so-called hereditary just infinite groups, and that one is branch just infinite groups. So this is one reason. There are some other. Next, so now I'm ready to formulate my first example, first result, sorry. Joint, take a branch group acting on a tree, spherically homogeneous rooted tree, so on the boundary of the tree, preserving uniform measure on the boundary. And assume that the group is branch. Now let X be delta t. We can take n power of X, and we can consider diagonal action, dynamical system consisting of G acting on Xn and preserving Mn direct product of n copies of mu measures. This is one dynamical system, but in fact I am interested in another one. Namely, here we have action of a symmetric group on n elements, and we can factorize. And similarly, we can take image of the measure. So in such a way, for n equal 1, 2, 3, we get a sequence of dynamical systems, actions of a group on this symmetrized direct product by a measure preserving transformations. And the theorem consists of two parts. First is joint Bartholdi me. It's 2000. That G delta T mu is totally non-free. So in fact, for every branch group, X totally non-free on the boundary of corresponding tree. Moreover, in this case, we don't need this subset of full measure. Different points have different stabilizers. Now, and I'm sorry, it is enough weakly branch, even in more generality, weakly branch. Not just for branch, but for weakly branch. Now, result due to Artem.co, young mathematician originally from Kharkov, Ukraine. Now postdoc in Stony Brook on a job market, by the way. So it tells us that for every n, so let G be weakly branch. Then for every n, then for every n, action is totally non-free. For any n, action G xn symmetric mu n symmetric is totally non-free. So we get a countable series of totally non-free actions. Moreover, if G is branch, not just weakly branch, but branch, then there is only countably many ergodic components. Countably many ergodic components for each n. And restrictions to them. So you can take the same n or different n's, and for the same n you can take different ergodic components, restrict to them, so you get ergodic totally non-free actions on that pieces. The corresponding characters in my notations here of G, which I recall are just measure of the set of fixed points, are distinct. So in such a way, we get a countable family of different totally non-free actions, and leading to different up to this quasi-isometry factor representation due to the fact that corresponding characters are different. They are indecomposable and distinct. So here we have one nice property of branch groups, that they have at least countably many factor representation, by the way, of type 2-1. Okay, I finished first half of my talk. Now it's clear that I will not formulate the result about spectra, but about space of invariant random subgroups. Again, let G be a countable group. Sub G in my previous notation, now I abbreviate just SG, set of subgroups. This is, can be naturally identified with a subset in this Cartesian product, Tikhonov product. Just you associate to a subgroup a characteristic function. 0 if element doesn't belong subgroup, 1 if belongs. Here we have the Tikhonov topology. We can restrict Tikhonov topology on this subset. It's closed subset. We get space of subgroups supplied by topology. It is compact, totally disconnected space, metrizable, and many interesting questions arise. Are there isolated points? If we delete them, are there new isolated points? What is so-called counter-Bendixson rank? When this process of deletion points will finish? What we'll get at the end, so-called perfect kernel, which will be empty if the cardinality of this set is countable, or a counter set otherwise. Now we have action of a group on this space by conjugation. Having a subgroup H and G by element G, it is sent to conjugate it. So we have topological dynamical system, group X on the space of subgroup by homeomorphisms. Invariant measures for these actions, any probability invariant measure for this action is, corresponds to invariant random subgroup. So invariant random subgroup is a random subgroup whose law distribution is invariant with respect to this adjoint action by conjugation. If a group is abelian, action is trivial. Any subgroup is, any measure, probability measure on the space is. So for abelian groups, this, if you have a normal subgroup and put a delta mass in normal subgroup, this will be invariant measure, fixed point, also not interesting. So mostly we are interested in ergodic, continuous, no atoms, invariant random subgroups. And problem 2 that I address, which group have such ergodic, continuous, invariant random subgroups. One can generalize this situation. So here, action by conjugation is action of the group of inner automorphism. So we are looking for measures which are invariant with respect to the action of group of invariant of inner automorphism. But you can consider the full group of automorphism of a group which is larger and be interested in those measures which are invariant with respect to this larger group. Or you can consider any subgroup in this group and be interested in finding measures invariant for subgroup. By the way, IRS of G is a simplex, okay, simplex of such measures. If we use the full group of automorphism, we call them Bowen, me, and Kravchenko characteristic random subgroups on G. So this is some subsimplex here. This is some subsimplex in the simplex of probabilities measures. Now, study of characteristic random subgroups is a topic interesting even for abelian groups. Because abelian group may have large group of automorphism, and yeah. So a few more results, and I am finishing. 3 minutes, yeah. Groups of polynomial growths due to theorem of Gromov are virtually nilpotent. They have countably many subgroups. They don't have ergodic continuous invariant random subgroup. So next question is, what about group of intermediate growths? Can it has many? There was example of a group which is branch, and due to result with Dudko, we know that at least countably many, because of this correspondence that I mentioned at the beginning, if you have totally non-free action, you can consider this map X going to stabilize the X in G, and the invariant measure becomes invariant random subgroup under this correspondence. So if a group has many totally non-free action, it has many invariant random subgroup. So the second theorem due to my former PhD student Ben Lee, me and Tatiana Nebeda, tells that there is a group of intermediate growth with continuously many, 2 to the aleph 0, ergodic, continuous, invariant random subgroups. Firstly, a few years, 5 years ago, approximately, Lewis Bowen shows that free group has many invariant random subgroups. And now we have stronger result, and due to Bowen, me, and Kravchenko, it tells that if you take free group of rank 2 or countable infinity, then it has continuously many, ergodic, continuous, weakly mixing, continuous, characteristic random subgroups. So, in comparison with previous results, that there are many invariant random subgroups, we can add that they are not only ergodic, but they satisfy the property of weak mixing, so free group X on the corresponding space weakly mixing, more stronger condition, and they are not only invariant random, but characteristic random subgroups. And from this result, we deduce that many geometrically defined groups like Gromov hyperbolic group of or mapping class group have continuously many ergodic, but this time invariant random subgroups. Not characteristic, but just invariant random subgroups. Thank you for attention.
Thank you very much. We have time for one or two short questions.
What is what you said about hyperbolic groups and multi-class groups at the end?
I say that as a consequence of this result is the fact that groups you mentioned have uncountably many ergodic invariant random subgroups. Ergodic are, by the way, extreme points of the simplex of such measures, and we have statements that in many cases this simplex is so-called Poisson simplex, the kind of the largest simplex. Simplex is Poisson when extreme points are dense, and it is unique up to a fine isomorphism. For instance, a set of probability measures invariant with respect to the shift is a Poisson simplex.
Examples of groups which admit totally free action and are not amenable?
There are branch groups finitely generated which are non-amenable. So they give such examples.